Okay, so for this problem, we have two charges. One's at the origin. I'll call this Q1, and then another one is over here, 2.4 meters away. So I'll call this distance D, and it has a value of 2.4 meters, and then Q2. And then the magnitude of Q1 is 2.5 times 10 to the minus 5 coulombs. Coulombs. Oh my gosh. Let me fix this C. Make it look a little better. Okay, so that's the magnitude of Q1, and then the magnitude of Q2 is 5 times 10 to the minus 6. Q2 is negative, but I'm just going to kind of put a negative here and a positive here so we can remember that. And then just write down its magnitude. And our goal is to find where the electric field is 0. I'm just going to double check that that's the prompt. Yes, indeed. Okay, so originally I was like, there's nowhere it's 0 because I know the field due to a dipole, and this is basically a dipole, and it's not 0 anywhere. But alas, Q2 and Q1 are not equal, so it's not truly a dipole. It's a dipole plus a monopole, which I did find a place where it's 0. So let's try to examine like the candidates for where it could possibly be 0. So let's note that Q1 is bigger than Q2. And so the field due to Q1 is going to be bigger than Q2. So let's kind of go through and figure out, first of all, in broad strokes, where the field is 0. So it could either be to the left of Q2, between the two, or to the right of Q2. Let's eliminate the easiest one first. So let's consider between here. So I'm going to draw these vectors in green to represent the electric field due to each one. So the electric field due to Q1 is to the right, because the electric fields always point away from point charges, and then if they're positive, and then towards the point charge if it's negative. And so that's from the positive charge, and then here's the contribution from the negative charge, which is going to be a bit smaller because it's a smaller charge, but nonetheless to the right. And so everywhere in between, this is going to be true. So not 0. Let's go to the left side. So here, let's say some random point here, or sample, representative, not random, representative point. So the electric field due to Q1 is going to be to the left, and then Q2, the contribution from Q2 at that point is going to be really small, not only because Q2 is smaller than Q1, but it's also much further. So everywhere along this point, this positive will dominate, and so that will be bigger. So this whole left region's out in the middle region, so that leaves this region. So somewhere in here, you'll have the negative charge will create a field to the left, and then the positive one, even though it's further, it has a bigger magnitude, and so it'll have a field to the right. So then they'll balance each other out. So we know we're going to be looking here. So let's find the distance from Q2 that makes it 0. So I'm going to call this some distance r, this distance r, and r is defined as where the field is 0. And so let's solve for that r by setting the force due to either of these, or the field from either of these, equal in magnitude, and solving for r. So the field due to 1 is just Q1 over 4 pi epsilon naught r, and then distance from Q1 squared, which is just r plus d squared. And then the field due to Q2 is going to be Q2, and then Q2 is only a distance r away. And then we also have the 4 pi epsilon naught. Didn't quite leave enough room to write it. Okay, and then basically I just did a bunch of algebraic manipulation. So cancel. I guess I can just write it. So yeah, so I brought Q1, the ratio of Q1 over Q2 to one side, took a square root. because if you bring that over, then you get r plus d quantity squared over r quantity squared. So it looks like that. And then if you take the square root, then that goes away. Cross multiply, blah, blah, blah. Okay, no, I totally lied. I'm not going to write out all the algebra, but yeah, you just cross multiply. If you're not sure how to do the algebra, I mean, there's like Wolfram Alpha that will walk you through algebra, and I recommend doing that, or else these problems will be much harder and tire you out. Okay, so oh yeah, and then r is d divided by this. So I guess I did show you one little step of algebra. Okay, that arrow got carried away. So r is equal to d over the square root of q1 over q2. Sorry for that fraction. The fraction's dying. Okay, so d is 2.4, and then these are our q1 and q2. And so when I plug that into a calculator, I got 1.94 meters, which is at least on the length scale of the problem.